Hello everyone and welcome to section 5.3. So in this section we're going to start talking about rational functions and understand some of the basic properties and some basic graphs of rational functions. In the next section we're going to graph more rational functions, more detailed ones. So a rational function is a function of this form where r of x is a rational function. It's a quotient, a fraction with a polynomial in the numerator and a polynomial in the denominator, right? So it's a fraction made up of two polynomials, division of two polynomials. So there's a few things to consider when you graph a rational function. You look at some properties. Because it's a fraction and it has potentially the variables is at the bottom, we need to worry about the domain. Okay, for a polynomial function, the domain is negative infinity to infinity. We don't need to worry about the domain because you can graph your function for any value of x. But for a rational function, we need to figure out where there's a problem with the domain, where the domain equals to 0. Okay, so you go to your rational function and you look at the denominator and you set it equal to 0. So we have 3 plus x equal to 0, and we get x equals negative 3. This is not in the domain. Okay, so the domain, so you say like this. So the domain is everything except this. So domain is all real numbers except that one, except x equals negative 3. Alright, so what you want to do when one of the values is not in the domain, what's going to look like in the graph, it's either going to have a vertical asymptote or it's going to have a hole. Right? So you could have like a circle hole in an otherwise perfect graph, or the graph breaks there completely. It could go in different directions, positive or negative infinity, and there's like a vertical line barrier. Okay, so that barrier, it's not really part of the graph. You graph it to kind of show that there's a barrier. It's not part of the function. But we want to figure out what's called the vertical asymptote. So the vertical asymptote shows the vertical line for the x values that are not in the domain. Okay, so to find the vertical asymptotes, you want to make sure that your function is simplified, reduced as much as possible. Right? Sometimes you need to factor it and cross out common factors from the top and the bottom. And then with the reduced function, with what's left over, the value that's excluded from the domain is going to give you the location of the vertical asymptote. So this function is as reduced as possible. So this means that my vertical asymptote, there's one of them, it's going to be at negative 3. Okay, so it comes from here. Right? So the domain does not include negative 3. There's a vertical asymptote at negative 3. Alright, let's look at part B. So part B, we want to see when the denominator equal to 0. So let's try to factor this. So 3x, x minus 1. And at the bottom, let's see if we can factor it out. We have 2x times x gives me x squared. And 12 is 3 times 4. 3 times 4. We need a negative 5 in the middle, so I think this is negative 4 and this is plus 3. Because that will give me 2x squared minus 8x plus 3x gives me the negative 5x and then negative 12. Right. Now the domain will be everything excluding the values that make the denominator 0. So the domain is all real numbers except So what makes these 0 are x equals negative 3 over 2 and x equals to 4. Alright, now for the vertical asymptotes. Alright, so we look at these values, we look back at our function, and we see if we can reduce it. Okay? If one of the factors cross out, then the x value that's not in domain that crosses out is not going to be a vertical asymptote. It's going to be a hole. It's called the removable discontinuity. If it doesn't cross out, then it's a vertical asymptote. Okay? So nothing crosses out. That means there's a vertical asymptote at x equals negative 3 over 2, and there's a vertical asymptote at x equals 4. So both of these are vertical asymptotes. So you can see that when you find the excluded values from the domain, those values could either be a vertical asymptote or they could be a removable discontinuity, which is a hole in your graph. Okay? So you decide which is which by going back to your factored function and see if it simplifies. If it doesn't simplify, they're vertical asymptote. If it does simplify, the part that simplifies is a removable discontinuity, a hole in the graph. Alright, let's look at part C. So part C, we have our function. I'm going to factor the denominator, x squared minus 1, x squared plus 1. Right, and you factor some more, x over x plus 1, x minus 1, and x squared plus 1. Alright, so the domain is all real numbers except for x equals, so we can see this is going to make the denominator 0 when x equals negative 1. This is going to make the denominator when x equals to 1. And this one never makes the denominator 0 because x squared plus 1 is never equal to 0. X squared is a positive number. If you add 1 to it, it's going to be even more positive, and that's never going to be 0. Okay? So you look, so these are not in the domain. You look at the function, nothing crosses out. That means they're both vertical asymptotes. So there's a vertical asymptote at x equals negative 1, and there's a vertical asymptote at x equals y. Okay? Let's look at part D. So part D, we factor at top and bottom as much as we can. So the top is x minus 3 and x plus 2. Alright, the bottom is 5, x plus 2, x minus 2. Alright, now don't reduce yet. Don't cancel things yet. You have to find the domain before you reduce the function. Okay? So the domain is going to be all real numbers except for x equals negative 2 and x equals positive 2. Alright? Now go back to this function. You can see that x plus 2 cancels out. Okay? This means that this right here is not a vertical asymptote. This is a removable discontinuity. Okay, let me scroll down so you can, I'm right at the bottom there. So it's a removable discontinuity. When you graph this, you're just going to graph the whole graph, but you're going to put a hole. So you're going to, at x equals negative 2 and whatever y value goes with that, you're going to draw like a hole within the function. Okay? So there's a hole there because x equals negative 2 is not in the original domain in of the function, but because we could cancel it, we could cross it out, then the function is actually not going to go to positive infinity or negative infinity there, so a vertical asymptote does not occur. Now at x equals negative 2, it stays there. It doesn't simplify out, so x equals 2 is a vertical asymptote. Okay? cool. So that was how to figure out what values are not in the domain and whether those values are vertical asymptotes or removable discontinuities. Okay, now we're going to look at figuring out horizontal or oblique asymptotes of a rational function. Okay, so we said a rational function is the quotient of two polynomials. So horizontal asymptote and where it occurs, or an oblique asymptote, it depends on the relative degrees of the numerator and the denominator polynomials. So can I have these rules in mind? So if n is less than m, so if the degree of the top is less than the degree on the bottom, there's a horizontal asymptote at y equals 0. Right? If the degrees are the same, if n equals m, then there's an asymptote at the horizontal line, y equals an over bm. So it's the leading coefficients. So the leading coefficient of the top one divided by the leading coefficient of the bottom one. If n equals n plus 1, so the degree of the top one is exactly one more than the degree of the bottom, then you have an oblique asymptote. An oblique asymptote is a straight line at y equals ax plus b. And you find this by doing long division of the polynomial. Yeah? If n is bigger than or equal to n plus 2, so if the degree on the top is bigger than 2 or more than the degree on the bottom, there are no horizontal or oblique asymptotes. Right? And the n behavior just sort of represents, if you take just the leading coefficients and you figure out that polynomial, it could be degree 2 or degree 3 or degree 5, then the n behavior resembles the n behavior of that resulting polynomial. Right? One more note is that a rational function never has both a horizontal or oblique asymptote. If it has horizontal or oblique asymptotes at all, it's going to be either horizontal or oblique, or you can have none at all. But you could have several vertical asymptotes and a horizontal, or several vertical asymptotes and an oblique. Okay, so vertical and horizontal mix, vertical and oblique mix, but horizontal or oblique do not mix together. Okay. Alright, so let's figure out, based on those rules, what kind of either horizontal or oblique asymptote each rational function has. Alright, so we're comparing the powers of the top and the bottom. So we're just looking at the leading terms. So ignore everything else. Right? So this is x cubed and this is x to the fourth. So this is the first case where the degree of the top is lower than the degree on the bottom. So we have a horizontal asymptote at y equals 0. Okay? So this is, with rational function, this is the end behavior. When you're finding horizontal or oblique asymptotes, you're finding the end behavior of the function. So it doesn't always go to negative infinity and infinity like the polynomial does. Sometimes it does, but most of the time it goes to a value. Okay? So when the degree of the top is less than the bottom, when x goes to infinity, y is going to go to 0. Let's look at part B. We're comparing the leading terms. So kind of ignore these. So the horizontal asymptote, the leading terms have equal degree. So the horizontal asymptote is going to be at the fraction of the coefficients. So you have y equals 2/3 is going to be the horizontal asymptote. All right, part C. This is the third case on our list where the degree on the top is exactly one more than the degree on the bottom. So this is going to have an oblique asymptote. And an oblique asymptote is a straight line. Y equals like mx plus b, or ax plus b, whichever you want to write it. So in order to figure out that line, we need to do long division for these polynomials. So we're going to take the top polynomial, put it under the division sign, and we take the bottom polynomial to put as the quotient, as the divisor, sorry. And to do long division, you divide the leading terms. So I'm going to divide 8x squared by 4x, and this gives me 2x. Okay, so this is the first part of the answer, 2x. Right, then you're going to multiply this 2x by both of these terms. So 2x times 4x gives me 8x squared. 2x times -1 gives me -2x. Right, so the next part is to subtract this from the top. So if I'm subtracting, I need to multiply by a negative number. So subtract this is -8. Subtract -2 is adding 2. So these cancel. This gives me 28x. And this one I'm going to bring down. Right, now you repeat the process. So leading term of this divided by the leading term of that. So 28x divided by 4x. This gives me 7. So we put plus 7 here. You take that number and you multiply by both of these terms. 7 times 4x gives you 28x. 7 times -1 gives you -7. And then we need to subtract. So subtract this. Minus a negative makes that plus. These cross out, this cross out. This gives you a remainder of 0. Okay? So this divided by that gives you the line y equals 2x plus 7. So this is the equation of the oblique asymptote. Okay? So yeah, with oblique asymptote, you have to go through this process of long division to find the equation of the line that describes the oblique asymptote. So horizontal asymptote is just a y equals a constant. Oblique asymptote, it's angled. So you need to find the equation of that angled line with that slope. All right, so let's look at some graphs. So we're going to do like baby steps of the graphing. So in this section, we're going to kind of look at some graphs to look at properties, sort of what did they look like, where do the asymptotes fit in, and we're going to do some graphing by transformations. The next section, we're going to do graphing by properties, which is kind of finding all the information. Right, so in these, we want to look at each of the graph that's shown. So it's like 3 different problems. We want to find the domain and the range for the function, any vertical asymptotes, any intercepts, any oblique asymptotes, any horizontal asymptotes, if there are any, okay? All right, so let's look at 30. Okay. So 30, if I want to look at the domain, I see that there are no vertical asymptotes and there's no holes. So the domain is all real numbers. So domain is going to be all real numbers. Or you can say the interval from -infinity to infinity. The range, okay, you can see that the range is divided in 2 parts. Okay, so the range is this portion. So the blue, the graph is the blue. The pink is a asymptote. Okay, so the dashed lines on the graphs are asymptotes. It's the solid blue line that's the graph of the function. So the range is this portion here. Looks like the lowest point on there is y equals to 2 and it goes to infinity. And for this portion here, it starts at -infinity and it goes up to -2. All right, and between there's nothing. There's a big gap. All right. There are no, actually, never mind. Sorry. There is a vertical asymptote, but it's not shown. Okay, so you can see how the functions are they're going up to infinity here and down to -infinity. They're not crossing the y-axis. Right, so this is actually a vertical asymptote. So there's a vertical asymptote at x equals 0. All right, that means this is not part of the domain. So the domain is all the real except for x equals 0. All right. There are no intercepts, so there are no x or y intercepts. No intercepts. The function is not crossing the x-axis or the y-axis. All right. I see a vertical asymptote at x equals 0. I don't see any horizontal asymptotes. I see an oblique asymptote here. Okay, so there's an oblique asymptote. Okay, at that line. So if we look at mx plus b, is the equation in the line. The b is 0 because it's passing through the origin. And the slope is, we're going down 1 and 1 to the right, so the slope is -1. So y equals -x is the equation of the oblique asymptote. Okay, let's look at the next problem. All right, so we're looking for domain, range, asymptotes. Maybe let's start with the asymptotes because we can kind of get them a bit better. All right, so there are two vertical asymptotes. So this vertical dashed line, so there's one at x equals -2 and one at x equals +2. All right, they're helpful for figuring out the domain. Okay, so the domain are all the reals except for x equals -2 and x equals +2. All right, now let's look at horizontal asymptotes. So horizontal asymptotes, you see this horizontal line here that goes through y equals 1. So there's a horizontal asymptote at y equals 1. And that helps with finding the range. Okay, so the range is going to be all real numbers except for y equals 1. All right. Let's see, are there any intercepts? Yes, there's one intercept right here. So this is both an x and a y intercept. So intercepts at 0, 0. All right. Let's look at the next problem. So let's start again looking at vertical asymptotes. So I see two vertical asymptotes, one here and one here. So at x equals -1 and x equals +1. That means those values are not in the domain. So the domain is going to be all real numbers except for x equals -1 and x equals to 1. I don't see any horizontal asymptotes drawn as pink lines, but like the graph is kind of doing this thing where it's kind of leveling off before it hits the x-axis. There's actually a pink line there, but there's a horizontal asymptote there. So there's a horizontal asymptote at y equals 0. And we can see that the range is all real numbers. So the horizontal asymptotes can be crossed by the function. Vertical asymptotes cannot because the function doesn't exist there. Horizontal asymptotes just tell you the long-term behavior. So like in the middle or even like out of the middle, you can cross it. So range is all real numbers, -infinity to infinity. Okay, let's see, there is one x-intercept here and a y-intercept. So the intercepts are at 0, 0. All right, good. So we can kind of start familiarizing ourselves with rational functions, what they look like, identifying asymptotes, and domain and range and good stuff like that. All right, now we're going to look at graphing these using transformations. And after we graph, using the graph to figure out domain and range and vertical, horizontal, or oblique asymptotes. So we need to be familiar with the basic rational graphs. All right, so we know, let me kind of go on the side here. We looked at the library of functions before, and we saw that y equals 1 over x looks like this. So there's half of it is sort of in the upper quadrant, and then the other half is in the lower quadrant like this. And it has a horizontal asymptote at y equals 0, and it has a vertical asymptote at x equals 0. Okay, so that's the basic 1 over x graph. Okay? And the basic 1 over x squared graph, okay, looks like this. It has that sort of same look, but then on the other side it's a mirror image. It still has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. Alright, so when we're doing transformation, we want to start with these pictures in our minds and then move them, flip them, stretch them, all that good stuff. Alright, so let's look at these. So 2 plus 1 over x. So you can see this is our parent function, so that's what we start with. And then there's a 2 added to it. Okay, so you graph the basic 1 over x graph, and then there's a vertical shift of 2 units. Right, so that means that the whole function shifts up 2 units. Okay, so including any asymptotes. Right, so let's graph the original one. So the original one looks like this, and like this, and it has a horizontal asymptote at y is 0 and a vertical asymptote at x equals 0. So if I'm shifting everything up 2 units, you want to shift the asymptote first. Okay, so the horizontal asymptote is going to shift up 2 units too. So you have this. And the vertical asymptote stays the way it is because there's no horizontal shift. Right, so basically these are going to move up 2 units. Right, so now we have our horizontal asymptote is here, our vertical asymptote is still here, but your function is shifting up 2 units to be above the horizontal asymptote and below the horizontal asymptote. Okay, so this has a vertical asymptote at x equals 0 and a horizontal asymptote here at y equals 2. Right, so the domain of this is all real numbers except for x equals 0, and the range is all real numbers except for y equals 2. Alright, let's look at b. Okay, so this function, the parent function is 1 over x squared. Okay, so 1 over x squared is the parent function because you see the square right here. The minus 1 in parentheses, this is a horizontal shift, so it's moved 1 unit to the right. Okay, so let's graph our 1 over x squared graph to see what it looks like. So it looks like this and like this. It has a vertical asymptote at x is 0 and a horizontal one at y equals 0. So we need to shift everything 1 unit to the right. So you start by moving the vertical asymptote and then the whole graph. Right? So let me erase and then redraw. Right, so the vertical asymptote moves 1 unit to the right, so it's going to be here instead. Right, but the graph is going to look identical, just shifted 1 unit, so it starts here, and then on the other side like this. Right, so now these are kind of, they have that vertical asymptote in between them, which is at x equals 1. Alright, so it has a vertical asymptote at x equals 1, a horizontal asymptote at y equals 0. That didn't change because the shift was just horizontal. The domain is all real numbers except for x equals 1, and the range is everything that's positive, right? So it's 0 to infinity. All right, let's look at the next one. So we want to identify the parent function. So I see 1 over x, all right? So 1 over x is your parent function. This plus 1, you're shifting up 1 unit. This minus 1, you're shifting a right 1 unit, okay? So let's have our 1 over x graph. Looks like this. It has a vertical asymptote at x is 0, a horizontal asymptote at y is 0. Okay? We have 2 shifts now. So the vertical shift is going to move the horizontal asymptote up to y equals 1. And the horizontal shift is going to the right, so that's going to move the vertical asymptote at x equals 1. Right? Now the graph just follows the original graph. You just sort of kind of pretend like the asymptotes are the x and y axes. So we're going to have a part here, and we're going to have a part here within those asymptotes. Right? Cool. So our vertical asymptote is at x equals 1. Our horizontal asymptote is at y equals 1. The domain is all the real numbers except for x equals 1. And our range is all real numbers except for y equals 1. Okay, let's do a few more of these. Three plus 1 over x squared, this is the parent function. So the parent function looks like this. I don't need to draw it that small. Let's draw it a little bit bigger. Right, so the parent function, 1 over x squared, looks like this. Alright, and it has a horizontal asymptote here, a vertical asymptote here, and horizontal asymptote there. So at x is 0, y is 0. We notice that there is a vertical shift of 3 units. So the horizontal asymptote moves up to y equals 3. The vertical asymptote stays where it is. Okay, so this stays where it is. And this one moves to 1, 2, 3. Alright, and then the graph follows. So we're still going to look like the same 2 branches, but it shifted up 3 units. Alright, so let's write what we know. So vertical asymptote is at x equals 0. Horizontal asymptote moved up to y equals 3. The domain is everything except for x equals 0, and the range is all the numbers bigger than 3, so 3 to infinity. Okay, let's look at one more. Let's identify the parent function. So this is parent function because it's x squared. It's going to be 1 over x squared. Let's draw it. This is the basic shape. It has a horizontal asymptote at y is 0 and a vertical asymptote at x equals 0. Alright, let me draw this a little bit better. Alright, so let's see. There we go. Alright, so shifts. There are shifts and there's also a stretch. That too represents you're doubling all the y values. So it's being pulled vertically. Okay? So there's a vertical shift, there's a horizontal shift of 3 units to the right, and there's a vertical stretch of 2. Okay, so let's draw our new asymptotes. So our x is 0 moves up to y is 0 moves up to y equals 1. Our x is 0 moves up to x equals 3. Okay, and the vertical stretch, what makes it is that if it's sort of like this, if I multiply everything by 2, it's going to basically look a little bit less steep. The curve itself, because where it was 1, 1, it would be 1, 2. So it's just basically, you kind of draw the same, but just a little bit less sharp. Okay, so we're going to have like this, and then like this. There you go. Let's write our stuff. So vertical asymptote at x equals 3, horizontal asymptote at y equals 1. The domain is all the real numbers except for x equals 3, and the range is all real numbers except for y equals 1. All right, let's look at one more. So we're going to take this and simplify it. So I can divide both by x squared. So we have x squared over x squared minus 4 over x squared, which gives 1 minus 4 over x squared. So our parent function is 1 over x squared. All right, so let's draw and see what that looks like with the asymptotes. So 1 over x squared has a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0, and its basic shape is like this and like this. Alright, so there's a bunch of stuff going on here. The minus is a flip. Okay, so this minus here is going to make the graph flip over. Let's do that a bit better. The 4 is going to make it stretch vertically. Okay, so if this is negative 1 over x squared, negative 4 over x squared is going to be stretched vertically. Negative 4 over x squared. Okay, so this is the shape of my function. All right, now this one is a vertical shift. Okay, all right, so let's start graphing it. So the vertical shift makes the asymptote go to y equals 1. There's no horizontal shift, so the vertical asymptote stays at x equals 0. Right? And the shape of the function is going to be flipped over and vertically stretched. So it kind of goes up here, and it's going to go down, and up here, and it's going to go down, like this. All right? That's what it approximately looks like. So we have our vertical asymptote is at x equals 0. Horizontal asymptote is at y equals 1. Domain is all real numbers except for x equals 0, and the range is everything from -infinity up to 1. Alright, so this is it for this section. We're familiarizing ourselves with rational functions in terms of basic shapes, vertical asymptotes, horizontal asymptote, oblique asymptotes, domain and range. And next section we're going to see more details on how to figure out the intercepts and kind of putting everything together. Okay?